All right. Well, cool. I want to start off just real quick. Who can give me a good definition of gravity? What we're dealing with. What is gravity? Anybody?
Gravity is what pulls us to the earth.
Absolutely. Absolutely. And here. Okay, so it's pulling us down, and anything can create gravity. We're creating gravity, right? Just the Earth is so much bigger that we're kind of sucked to that. But if you took two of these desks and put them out in space, way out there by themselves, they'll kind of stick together over time with gravity, right? Now, here's a sort of a different question. Why do boats float? Yes?
Buoyancy?
Right. Buoyancy. Now, buoyancy is... Oh, bonking people in the heads already. Buoyancy is where basically what you're having to deal with is a ship sits down in the water, right? It's usually hollow, there's people inside, there's cargo inside the ship. The part that's under the surface of the water, that whole, the outside of the hull, the people, the fuel, all of that, weighs less than the amount of water that it's taking up, the displacement. So as long as you've got a boat that weighs less than that amount of water, it's going to float. Which means you can make a boat out of steel. They often do. You can make a boat out of concrete. As long as it's got some airspace inside, so overall it weighs less. So if I get two balloons and I take one of them, blow up a balloon, tie it off, and let go of it, what's going to happen to it?
It's going to float. If you tied it up.
Yeah, I just blow into it.
Oh, then it'll just...
That would just go down.
Right, it's just going to go down. I take one with helium, put helium in it, tie it off, and it looks like everybody's going to know this. What happens when I let go to it?
It floats up.
It goes up. Because the helium weighs less than that amount of air. Now the balloon that I just blew into, what am I putting into it? I'm putting in
Carbon dioxide.
this carbon dioxide, I'm putting all of this stuff in that's in the air here, right? So it weighs the same. It's the same thing. When I put in a lighter than air gas, it wants to go up, mostly because all the other air around it is saying, hey, get out of my way, I want to be down here where gravity is pulling me, right? So all of this air above us, we've got miles and miles of air up above us, pushing down on us. It could crush us, except that it's pushing in all directions and kind of pushing out so we don't get crushed. But it's pushing down on this lighter than air balloon and kind of forcing it to shoot up into the air. So as you go up in space, gravity is pulling all the air down. The air gets thinner and thinner and thinner. Now there isn't a spot in which you can say, oh, we're absolutely in space. Everything just gets thinner and thinner. I'll get this cool little sight out of the way. There's a mouse here somewhere. So, we've given fancy names to all these different layers of the atmosphere. We've probably talked about them. Different layers, and they keep going up and up. Now let's see, that's 40 miles. So the space station will be about 60 feet up there. Way, way up there. Space station is around 250, 300 miles up. But there's still stuff around it. It's very, very, very thin, but there's still air around it. Matter of fact, they have to keep boosting the space station every once in a while with rockets to get it back up again because the air is blowing on it, slowing it down, making it fall back to the Earth. So everything gets thinner and thinner and thinner as you go up. So there is no surface like you would expect on the ocean where you say, oh, that's water, this is air. It just gets thinner. So what we're going to be doing with these balloons, for example, one of these, this is one that blew up. It's awesome. One of these balloons, we're going to be releasing it here on the ground. It's going to be lighter than air. It's going to be so much lighter that it's not going to only be able to carry itself up, but it's going to carry something else with it, whatever you guys dream up. And it's going to go up. Now, how high is it going to go? Well, that depends upon the thickness of the air in this area, and a certain day that we launch it, the weight of everything pulling down, and so on. But it's going to go up roughly in here. Now, what's cool is that's 3 times higher than most any human has been. The folks that have ridden in jet planes, right? So you yourselves are going to be building something that's going to go 3 times higher than anyone else that you know has done. Higher than Mount Everest, higher than anything else that we've built that stick to the ground. Pretty cool, but it won't be in space. There is a line about here that they call space, only for the people who get these little special wings that say, I've been an astronaut. And that's at about 52 miles or so up. And that's kind of a rule that some politicians made of what's space and what isn't. But basically, if you're up on the top of Mount Everest, you need oxygen to breathe. There's oxygen there. There's air there. You're not going to explode. But you sure don't want to be climbing a mountain with that little bit of air. So you need oxygen tanks. Well, up here, there's only going to be 1/100th of the atmosphere you've got here. So keep that in mind. We don't want to send any animals up there unless you like making really perfect spacesuits for these guys, because there's not enough air. We're also going to be dealing with some really interesting temperatures where the temperature will start dropping, then it will level out and start rising again. We're going to be above all the weather. Stuff we call weather all happens down here in the tropopause. Right after the troposphere, the tropopause is the point where there's no more water up here. So we're going to be up where it's incredibly dry. So what kind of things can we send up there? Well, first I want to talk about a little bit of how we send stuff up there. I'll just take a few minutes on this. We've got these huge balloons. Big old latex balloons. You can see here we are at a school filling it up. We often use helium or hydrogen. One of the things that we're going to do for this event is we're going to use hydrogen. Now, hydrogen likes to react with oxygen and make water. But when it does so, it goes boom. So we're going to have to take some precautions with that. Helium is completely safe and fine. But helium doesn't exist naturally on this planet. It's called helium because the first time we discovered it, we were looking at the sun, at Helios, and said, hey, this is a thing that's on the sun. We'll name it after the sun, Helios. We didn't know it was here. It wasn't until we started digging in the ground and pulling oil out that we found helium bubbling up through from the radioactive decay in the center of the Earth, the stuff that keeps the Earth warm. So we only have a little bit of helium left on this planet. We're running out of it just like we're running out of oil for the same reason. We're emptying it. So we've decided not to use helium because we want to save the helium for those scientists that are doing some really cool stuff and need it. We don't need to be sending it up in a balloon and just popping it and letting it go loose. So we'll do hydrogen because you can make hydrogen real easily. You can take electricity and run it through water and it will split into hydrogen and oxygen. It's a great experiment to do here in class too. So it's pretty easy to make, real cheap, easy to get hold of. So we fill that up. We've got a little package. We've got a little parachute. This thing's been up 11 times. Pretty beat up. And, we've done a lot of these different things. There's my 11-year-old going, to the camera. And we put onboard cameras, all sorts of cool cameras and stuff on there, and send it up. Durham, the next county over, their library system is the first library in space, FLIS. It's my shit. And we're going to, release it. We'll do a countdown. We'll have you guys release the balloon at designated time. We'll have the launch safety officer make sure that everything's clear and there's no airplanes around and things like that. We'll head up above the weather. So you can tell from here that we're already past the troposphere, past that tropopause line, starting to go up into the stratosphere. It's kind of weird up here. The sky isn't blue. Yes?
Because in the ionosphere, that's where the little ion particles are that make the sky blue. Like, is that what you're thinking?
Close, close.
Because only the color blue can go through the troposphere.
No, we're getting into college physics, so let's see.
Isn't there light that makes color that hits an atmosphere that spreads that blue goes through easier than other colors and spreads out easier? That's
Right, right. So what's happening is, try not to hit you. The light particles are coming in, and as the atmosphere gets thicker and thicker, it's something called Rayleigh scattering, where the photons are actually getting scattered and shifted around, and they're actually making the air particles glow, very similar to the glow that's up in here. This is Mercury, so it's glowing white, but our air particles glow blue. Now Mars, the sky is red and the sunsets are purple, because it's carbon dioxide. It's a different atmosphere, different colors. Very cool. So down below, there's a lot of air. That light hits it and makes it glow. Well, we're going to some place where there's so little air that Rayleigh scattering isn't happening. We're going up to where oxygen is ozone, O3 instead of O2, which is very important to keep us alive. So you'll notice as we go up, the sky is getting darker and darker. Yeah, that's a duck. I gave him a helmet. He's got a little microphone and a helmet. So this is, let's see, I think Burlington is about there. This is awesome. This is cool stuff. But you notice it's dark up there. You can see just how thin the area of breathable air is around our planet. Oh, no clouds that day. Very, very thin layer of atmosphere. 40, 85. RDU Airport, Durham. That is Hillsborough. Hey, Burlington. Greensboro, Winston-Salem.
Where's he on?
Elon would be, it's that tree area right there. All those trees. So we're going to have to go up and get some photos, see what you can spot from up there. Now you've got an airport, huge airport that just shows up as a little line. All of Raleigh is just this. That's pretty crazy. So what we've got is we're going to be sending stuff up. We're going to be tracking it. We've got these cool little devices. Probably the most expensive part of the whole thing. That will transmit locations. And we'll have some of you guys running mission control and tracking and coordinating where, based on our plots of we're going to leave Burlington and go here, and then making sure that the balloon's coming down this way and the cars to go get it are going to meet. So that's going to be interesting to do. Now, we talked about the gas in the balloon is lighter than the air around it. When we release it, is it going to go up and hit the space station? No, because it is going to rise up to a point. The air is getting thinner and thinner and thinner. It's going to reach a point that's similar to how a boat floats on water. It's going to finally reach a point where the weight of the gas inside equals the weight of that same amount of air. Now right now, it doesn't feel heavy to us down here because it's coming in from all directions. But this air is really heavy. So it's going to head up until it reaches that point, and it's going to float. Well, there's one other problem that we've got to factor in. As we go up, the air gets less dense. And we're not putting this into a big metal ball. We're putting it into a piece of latex rubber. So it's going to stretch and go out. So this is a picture from overhead camera down on a cloudy day, taken from this one actually. looking up at the little balloon that we just filled up right when we let go of it. It's about 6 feet around. Yeah, this big around. As it goes up, it's going to reach a size where the balloon rubber has stretched to the size of this room. Now at that point, it's going to fail. Boom. It's going to pop. It's going to turn into lots of little shreds. Don't worry about it. This stuff dissolves in the environment after just a few weeks. It's very biodegradable. So lots of this stuff will be coming down, landing all over the place, but it will dissolve really quickly. This is a piece that was still tied on that came down. There's a bunch. We're going to have to make sure we engineer something that prevents this from tangling our parachute. Because if this is up here, oops, it's coming down like a rock. So, check this out. These are 3 successive images from this camera. So, 1/30th of a second apart. So you can see this tear starting to go and see it blow up. So that's going to happen at some height. Now we can guess what the height is, but if there is an imperfection in this when they design it, or I don't know, one of us accidentally touches it before it launches with our hands, the oils on our hands cause it to dissolve, or who knows. As it goes going through a cloud, a piece of hail scratches it, it might fail early. Or we might be lucky and it might fail late, which means it's going to go higher than we expected. We don't know. We can make a guess. And we can plot out our predictions based on that guess, but we never know. It may pop sooner, may pop later. This is right after pop. Poor duck needs to hang on. So then the thing's going to come down on whatever parachute. And we hope that this mess, flapping around up here, doesn't get tangled in this. Now, when it first pops, it's going to come down. Remember, the air is really, really, really thin. So the parachute might open. It's not going to do anything, because there's not enough air to push on that parachute to make it really do anything. So it's going to fall at about 200 miles per hour. So it might take, let's say it takes 2 hours to float up there. It's going to fall in about 15 minutes down most of the way. Because up above the troposphere, there's just not enough air for a parachute to do anything. You can make a huge parachute, might slow it down a little bit, but then once you get down into the lower atmosphere where there is air, that huge parachute, you're going to drift out to sea, because it's just going to take forever to come down. So one of our design considerations that we'll talk about later is, okay, you've got a big heavy wad of balloon that may or may not be up there that's tumbling for 20 miles straight down at 200 miles per hour with a parachute. The parachute isn't really going to do anything. So we want to make sure that our payload, our package, can survive tumbling and falling at 200 miles per hour. Like the guy who jumped out of the balloon, high altitude, and he went into the spin and all of that. That was dangerous for him. Because if he spun too quick, there's nothing he could do with his hands or anything that would control him. If he opened his parachute, it wouldn't do a thing. If he spun too fast, his head would pop off, literally. So, you've got to take all of this into consideration with your design. All right, the thing's coming down. It's down into the troposphere. It's down in the clouds. There's enough air. The parachute has opened up. It's now drifting and blowing with the winds. You're coordinating, or you're on the chase crew. Here's our car right here, because we got close with this one. One of these days I'm going to catch it. It's going to be cool. And then the thing comes down flat, somewhere. Hopefully you want it to come down slow enough that it doesn't break somebody's windshield or, hurt somebody, right? We have no control over where it's going to go. But I can tell you one thing. Big, gorgeous, beautiful field. It's going to land in the one tree in the field. Because they get sucked into, I don't know how many rockets you guys have done, but they always seem to get sucked into trees. So I've spent time with waders in swamps, canoeing out and then having to swim to get at one, hanging in a tree 3 feet over a swamp. Big field. Yeah, it was in that one tree. So then we got to figure out, for the recovery team, they got to bring some poles or something to try to get it down. That's the fun part. So there's a lot we can do mathematically to predict stuff. There's a lot of great data you guys are going to be getting out of these. You can figure out what's going on. I mean, look at this. That's the track, looking at a map of what it did that day. Because as it was going up, it kind of spiraled in the wind. That's crazy. So we'll be able to get all sorts of incredible information out of this. So, we'll notice things like the wind blowing it. And then it gets to the point where it's above those high-level winds. And it just stops and floats straight up until it pops. And then, zoom, rides down at incredible speeds until that parachute finally opens. And then the wind catches it again. And it comes down to its landing. So, I've got some videos I can show here of, there's another crazy one we did just the other day, a couple of them. There's one at Burlington in the wintertime. Jet stream. Very strong winds in the upper troposphere, right? I had a picture of an animated version of it earlier. During the wintertime, the jet stream's really whipping. The ground winds go east and the jet stream goes east, which means your balloon, if you released just a normal-sized weather balloon with your payload here today, it's going to be way out in the ocean because of that. Now, springtime rolls around and the winds change. It gets warmer here. The ground winds still blow east. The jet stream reverses and goes west. And you end up with releasing it. It goes up, turns around. This case, it did loop-the-loops. Blows back, pops, and then comes back down. Midsummer, if we did this in, over your summer break or something, then we could run the chance of releasing it. It goes up, blows overhead, pops, comes right back down on you. So, it's a possibility. We've come within like 4 miles of launching and having it come back. So, we're bound to get some really cool pictures. Let's see what kind of videos we have. You've seen the videos from the Maker Faire. Here's another school launch. One thing that, I don't know if you guys have seen this. Let's speed it up a little bit. So here's all the parents getting the balloon ready. Hey, I know that guy. Setting up the balloon. Okay, here we go with kids holding onto strings, holding it down. Bye-bye.
All right. So remember what you're going to do? When we say lift off, you two let go. You two hold on.
Where did my mouse go?
All right.
Get my mouse.
Let go.
And you know what? You see how tangled this string is? Just laying here on the ground?
That's going fast.
It's going to untangle itself.
It's twisted though.
Which means you probably don't want to watch that video if you get motion sick, because you're just going to be spinning for 3 hours going up. There's I-40. Yay.
Really?
You can hear the wind. Yeah, you have a
How
question?
fast is it going when it's going up?
Usually we send them up at 5 meters per second. Oh, I just heard a camera click. So we've got cameras and things like that on board. Speed it up a little bit more.
You can see the earth starting to bend.
The winds are blowing different ways at different altitudes. Maybe you can fly up through a thunderstorm, an April thunderstorm. That would be interesting. You guys know what the hail inside a thunderstorm makes lightning, right? Imagine this thing. So we're going to have to make sure that our range safety officers in the crowd are able to look at the Doppler radar and make sure we don't have any spring thunderstorms. Try to launch between the clouds. Oh.
Nah, I'm good.
Here's
Look
the,
away.
Exhausting.
yeah.
You should do it full screen.
Yeah, you keep looking at it.
No, it doesn't like full screen. What's it called here? Oh.
It's like a roller coaster.
Yeah, it really is.
I love roller coasters.
Me too.
Oh my god, I love to just
So-
go.
Let me stop that and show you one that. So this was one that we were trying to win a world record with. It was a competition.
Did you win it?
This competition, we won it with this launch. Guess what? They're doing that competition again next year.
Oh, maybe we can.
Wonder when it's going to be going on.
When we're doing it.
And they've got like 12 different ways you can win this year, not just altitude. So, like the most people involved, the most kids involved, the most balloons launched. There's all sorts of things. And some of it has to do with you guys being able to fill out the reports, making something that looks like an official scientific report after the flight. The coolest experiment, most interesting experiment. So here's us back down on the ground with my son again. As this thing is going on up, I'll let this run a little bit because I do the entire launch on this video. Yes, sir.
Will that balloon eventually dissolve, like, since you've touched it and all that?
Yeah, it is definitely, and any of you guys that don't have a latex allergy, if you want to play with it, it will fail. It'll get brittle. Have you ever seen like an old newspaper or something, old book where it kind of falls apart on you? It will do that. And when it's outside, the sun will really tear it up.
Let's see.
Look, I have two cameras on board. One looking like this and one looking like this.
I'm tired.
That's the ocean. That's the Atlantic Ocean. Yes, sir.
Pass it back. Guys, pass it back.
We'll see. I'm going to ask some questions first. So, what we're going to be dealing with... Yes?
You know how you get really cool pictures from these? Does NASA use some of those pictures for like space books?
Well, this is all cool stuff, right? NASA's been doing this since the beginning of NASA. We've been doing this with weather balloons. Let me let you in on a secret that maybe won't make this as cool as we think it is. They launch 2 of these every single day from the Greensboro Piedmont Triad Airport over in Greensboro. One down at the coast every morning, one in Greensboro. So every day, 4 of these things are launched. So they have almost 100 years of this stuff. Now, what they don't have is the cool new tech we've got. So. Okay, here we go. It's upside down because what I did on this one is I put the balloon, then the package, then the parachute. So when it popped, it flipped upside down. That was my way of keeping the balloon and the parachute away from each other. Okay, here it comes down. And listen, you can hear it. No, don't hit the car! Boom. Yes, the parachute hung over the tree. The one tree in the whole area.
Oh, that's awesome.
And that's all it was. Since we were going for high altitude, we want to make it as very lightweight as possible. Yes, sir? Yes, absolutely.
She said they excuse me?
This line here? This? Oh, these. Those are showing the super high level clouds. Does anybody remember their names of their various types of clouds? You know, like this one, so obviously it says cumulonimbus, right? Those are the thunderstorms. You get that thing they call a beaver tail at the top, the anvil cloud. Question? You know the name of those?
I think it's either cumulus or stratus.
And stratus because they're very close to the... Right.
And I have
So,
a question.
yes, absolutely.
If you were to, if it hit somebody in the head and it gave them a concussion, would you get sued?
Yes. Which is why I'm going to be your consultant. I'll be telling you how you could do it. You guys will be letting go of it. So yeah, that is a very good question. So what do we need to do to make sure that it's safe? Now, some of the things you guys are going to do is look into the stuff that the people who fly the planes say is legal. You know, can we send up a missile? You know, can we send up bombs? Can we send up something that's on fire that's going to fall into a woods? You know, there are some rules that you guys will be learning about on the design of this. It's the design shape is based on what they think might smash the windshield of a jet. So we're going to be making sure that everything is safe here. Now, to get high altitude, you want it lightweight. There's your hint there. So the question is, how can everybody be involved in something and build something but still be lightweight? Maybe the answer is send a bunch of them. So we'll be looking into that as well. So yeah, that's very much a concern.
So how does your video camera not run out of battery or?
Well, they do. They do a lot. This is one of the cameras. This has on board, it only has about 50 minutes worth of battery. This one has about 30 minutes. Here, let me turn it on. So I add extra battery packs to these. You ever seen got cell phones and have those extra battery packs that make your cell phone last longer?
Yeah.
We kind of stick those into the back as a supercharger, give them extra time. Okay. Say hey, everybody. So this is recording right now, and this is, a lot of those pictures were filmed with this very camera itself.
What kind
So,
of camera is that?
this one is, it's a little dash cam, like the Russians use in their cars all the time. This says it's sold as a keychain camera as well, and there's lots of different models of these. You could go with a big, one of those fancy GoPro cameras, but I can get 4 of these for the cost of a GoPro, so, you know, that's up to your budget. Yes?
Wait, 2 questions about those cameras.
Yep.
What are the quality of the cameras?
These 720p high def, this will do 720 and do full 1080. I put it on 720 because it takes up less space on the little chip, and it's also easier to edit because 1080 is bigger than my screen on my computer, so it's kind of hard to look at it, edit it when it's, you know, it's big, full screen HD video coming out of this. So,
Also,
cool stuff.
Like, in the videos and the pictures, I noticed that when it was high up there was sort of the spherical shape of the Earth. Is that just the field of view of the camera, or is that the actual spherical shape?
Some of it is the curvature of the Earth. You're getting up high enough where you can see it, but honestly, majority of it is because these are fisheye lenses. These are wide-angle lenses. So this particular lens here, and this one is the same, can see from here over to there, 120 degrees. And if you're looking at a surface and tip it up just a little bit, it kind of bends the surface. You know, if you tip it down, it'll look this way. So you're absolutely right. Majority of that curvature that you see is a result of this. But it looks cool, especially when you consider that, no, some of it, if you were up there, you would actually be able to see the curvature of the Earth. And from that curvature, you could measure and determine the whole diameter of the Earth. You could tell the size of the Earth just by that one photo. So, yes, sir.
So, when these weather balloons go up, are they gonna stay above like the above the ozone layer, or where are they going?
They're going to be right in the midst of the ozone layer. It really depends what your design is. If you want to put a whole lot of really cool stuff on it, it might only go to here, in the middle of the ozone layer. But if you make it really super lightweight, it will go up above it. It'll punch through above the ozone.
Where did your world record?
104, right up here.
Yeah.
Yeah. So I've been to 142,000 feet. With all the cool stuff we're probably going to end up doing, we'll go to about 100,000 feet. Yeah.
Have you ever sent one into the mesosphere?
No. The problem with that, again, is that buoyancy that we were talking about. When we send the balloon up, the thing that's pushing it up isn't the light gas wanting to escape the Earth. It's the heavier stuff around it going, get out of here, pushing it up. Well, the air is getting thinner and thinner and thinner as it gets up there. So the highest weather balloon has only been to about 50 kilometers up. Above that, there's just not enough air. And that's part of what they call the stratopause. There's a few tricks that I'm working on, top secret tricks having to do with how the air undulates into storms down here can cause this to heat up, which will make your balloon go higher. Some tricks that you can play to try to get it up higher. But no, that's where we want to go. Of course, one of the cool things would be, what if you took one of those rockets and put it on a balloon? That rocket's only going to go 300 feet, 500 feet on the ground here. What happens if you launch it here? It's going to go much further because there's not that much air on there. But then you start getting into problems with those little fins aren't going to do a thing. You're going to need fins this big on a rocket that size to keep it stable and going in the right way. And we've got to work with the legal side of it too. But
Yeah.
yes.
Yeah. Why do you have to have one of those like packets?
You mean why don't you just have all your equipment out? Or why do you need a box? You don't. Think about that with your design. You don't need to have a box. I do it because it just makes it self-contained. You can have everything out. You know it's going to be really, really cold up there, so you got to keep your stuff warm. You can do that. You don't need a box. You can do whatever. The world's largest. Yeah, quick.
So say if you were to attach rockets to it, you literally need fins because if you just angle one rocket this way, and launch it, you can keep it on that same.
Or spin it. Like a bicycle wheel spinning keeps you upright. You spin the rocket and then launch it. It stays stable. You have thrusters, like you're talking about, that can counteract it. There's a lot of cool stuff you can do. Good.
Can you see like whenever like you're looking at the sky, can you see
The atmosphere? Absolutely. Absolutely. Some of these pictures, I've adjusted them, kind of photoshopped, to be able to see the roads on the ground. But as you're adjusting it, you can see all the different layers of the atmosphere. You can definitely see where the clouds are, the tropopause, because of all that water in there. You know how hazy it gets in the summertime here, but in the wintertime the sky is that beautiful dark blue, but in the summertime it's Carolina blue. Sorry, I went to state. So that you can definitely make that out. Way back there, you've got a question?
Have your balloons ever landed in the ocean, and if they have, what was in it?
Sunday. This past Sunday, I drove up to Asheville, up to the mountains, to try a new experiment with high altitude in my transmitter. I did something wrong. I've still got to finish. I did the math, and it looks like it's right, but it only went up half the speed that I expected it. I wanted to go at 3 meters per second, and it went about 1.7 meters per second. Let me pull up our projection. Yeah. Entire state in 7 hours.
What was it?
was a very small, again, I was going for height, so I was very lightweight. It was about this big. It had a special ham radio transmitter. I've been working with a ham radio guy in China to help build the thing. It's so small and lightweight. And it had, and one battery that controlled it, and the guts that is inside this. I opened this up and pulled out the camera part, and just had that in there. The whole thing was, the entire package weighed less than this. It was 110 grams. And it had the largest balloon I've ever launched on. Big, big, big balloon.
So how they stretch even more than regular.
That's when you had.
Exactly. Oh, well.
That's the problem.
Yes?
So, you know how you said there's going to be like multiple records? Is one of the records like how fast it raises up or like how fast?
There are, and we could pull up the global, what's that say on this, the badge? This will be the second annual. This
Global
is
Space Balloon Challenge.
Global Space Balloon Challenge. So you can go and look at all of the different things that are involved in that.
And I've already been on that site and have downloaded the application because we will be launching during
The
the
window.
time span that they're
Coincidentally,
allowing.
you know, who knew that it was going to be on that date? Except a member of the group. Anyway, so it just happens. Last year they tried to do the entire thing on a weekend, and the whole East Coast had thunderstorms that whole weekend. Everybody launched all over the world, except we couldn't. And they gave us an opportunity to catch up the next weekend. You know, everybody agreed to it and all of that, and that's where we won. So, yes.
So, where is the place the astronauts? Do they go to like real space or just like...
So, in order to get your astronaut wings, your little thing that says, yes, I've been in space, you have to go above 52 miles. So that's off the top right here, right? So that means that those guys out west that are building the craft that will go up and then fly back down, the people who ride on those ships, Spaceship 2, Spaceship 3, those things, they'll be able to get the little wings, a little, you know, hey, you've been in space. Is it really in space? Well, if you open the door without a spacesuit on, yeah, you die. So it's above the line at which the atmospheric pressure is so low that your capillaries in your skin explode without a spacesuit. So not a nice place to be. You can go up to Mount Everest and be just fine as long as you stay still and every once in a while take a breath of oxygen, right? Just keep you from passing out. You know, Denver and some of those cities are, you know, down here. They're pretty high up compared to us down here at sea level. Once you start getting up in here, though, water does some weird things. It gets real cold, and water can actually sublimate, which is directly boil. And that's not good for people that are made out of mostly water, right? So, now, our space station, International Space Station, is 300 miles up. This morning, out of Florida, we launched a spacecraft to 3,000 miles, past the radiation belts of the Earth, turned it around, and successfully landed it in the Pacific Ocean about an hour ago. So that's 3,000 miles. But, and you guys watch DirecTV? That's 23 to 25,000 miles out to that satellite that's beaming to your house. The moon, 500,000 miles. Philae, the little thing that was the little probe, 300 million miles away. We landed it on the comet.
We have about 3 minutes left.
Cool. Last questions.
So why couldn't you just put a balloon on there and a blown up balloon? Because when it hits, as you said, it pops and expands, the other balloon would expand and keep going.
Oh, so put like one inside the other or something? Oh, put two balloons on.
Yes.
I tried that. One of the problems with that is you've got this, the balloon acts as like a parachute on the way up. the actual sphere of the balloon just kind of slows it down. All the wind blowing on the top of it. So you add a second one, and you end up with the first one having to tug to get the second one up there. And they're all both expanding. So you could set it up so that it goes up to here, the big one, you know, the one that gets the biggest and explodes, and then the second one might not have enough lift to keep the thing going again. So you might end up with what's called a floater. The thing will float. And it's a great way if you want to send it around the planet. Matter of fact, there's this little company called Google that is taking these, and the bigger ones of these, they're putting wireless access points on them, and they're planning on sending them up and having them float all around the planet. So that no matter where you are, you've got Wi-Fi coverage. Because are they satellites? No, they're in the air, they're floating, right? One of my friends over in England took those little Mylar party balloons. He let go of it in July. It's got a transmitter on it, a solar panel. It's still going. He's been around the world 8 times with this little toy balloon. Now, it only went up to about here and kind of hovered. But it's been all the way around the world. The last few questions. We're running out of time.
What was the farthest the balloon has ever been? Like
distance?
Pops, yes.
Sundays. Yes, sir.
So what was your experience going above the mesosphere? What was it like going
What is above the
to
mesosphere?
near space? Yeah, what was you? What
Well,
was
near space is kind of a cool name we give to this. This is space, right? The official legal space, right about here.
And you were there.
We call this near. Well, my camera was there.
Oh.
So,
I have a question.
yes,
So how did you get involved in this hobby and this citizen science project?
I do high power rocketry. You know those rockets? Mine would just barely fit in here. Big ones. Because I used to do those when I was your age. Lots and lots of those. So, bigger, I get to do the bigger rockets, you know? Let's take about $500 to $1,000 every time we launch it. Whoosh. Yay.
One lucky person.
Yeah. 10 minutes, 5 minutes for the launch. $1,000. For $100, I can send this thing up for 4 hours. Orders of magnitude higher than I could ever dream of with a rocket. Take some really cool pictures. Hey, on the way down, I like doing geocaching and hiking and going through the woods. I get to get out my little thing, a compass, and try to find the thing, doing geocaching in the woods. It's like 5 different hobbies all together in one. So, it's a very cost-effective way to do it. Way back there. Sir.
How far could a regular balloon make it up?
Oh, you mean like a little balloon?
Yeah.
About 20,000, 30,000 feet.
Like,
Then they'll
where would
burst.
that be on the nappy thingy here?
About here. Because especially if you blow it, when we launch those, they're kind of real floppy and almost empty. But you blow up one and release it, it's going to go up to about there and pop. And remember, the little rubber ones, they'll pop and land in the woods, or the sun will dissolve them. The Mylar party balloons, those things stay up, as you know, they've been around the world 8 times. They stay up for a long time, then they come down in the ocean, and animals think they're jellyfish, and they eat them and die. So try not to let go of those aluminum party balloons, because it kills a lot. If you go down to the aquariums, you'll see where the doctors are always working on the sea turtles, those endangered sea turtles, and almost all the time they're pulling those aluminum balloons out of them. It kills them, because they get stuck and they can't eat anymore and they starve to death. Yes?
All the balloons you launched, what is the, how many miles is the, how far did it go up?
On
Like
you?
the tallest?
For the ones we've done? Or, in kilometers? So just under 30 miles, 25 miles straight up. Really cool. Okay.
Last
Yes,
question.
last question.
So, Sunday, how do you estimate it will develop?
Well, the balloon parts will probably, especially in the ocean and the salt water with all the animals picking at it and stuff, it's probably mostly gone. The little styrofoamy thing, wrapped in lots of black tape and stuff like that, probably going to be 6 months. you know.
Are you still able to track it to the GPS?
No, the battery died on it, as it should have. You know, the battery is only good for about 5 hours or so. That's all. It was only supposed to go 4.5 hours and land here, you know? It's supposed to land here. Yeah. So we need to make sure that, you know, what happens during launch time if there's a weird freak storm that brings the jet stream down to us?
Oh no.
And we, huh?
Do you want to show that website with the jet stream that you had up?
Oh yeah. So, you know, since we're launching at the mall for the Makers Faire, we can't say, oh, we want it to land in this big area with lots of open fields, right? So in order to do that, we need to go over there to launch because of the winds. We're going to be launching from a fixed point, which means at this point, we have no idea where it's going to land. Is it going to be in Virginia, South Carolina, Tennessee, the Atlantic Ocean? We don't know. So that day, we're going to have to make some calls. So this is live. Let's pick, here's the surface winds. So not much. It's a calm day out. Right? And we're right here, right? Well, let's go on up to the upper jet stream. That's booking.
That was powerful.
So we release here now. We're going to the Bermuda. We're going to the Bermuda Triangle. Bahamas.
We could go to Canada.
Let's go even higher. And again, totally different in the spring and summer. So
We'll have to get that website.
yeah.
Well, we want to give Mr. Lowell a round of applause and thank him.
It's going to be great.
And we're really excited to work with Mr. Lowell and have him help us, you know, together and give us some advice and as we move towards the spring launch. So now, Mr. Lowell, you may not know this, but before you leave, you have to get a picture with all of our students. So.
Okay.
The Alamance Makers Guild is a group of talented and creative makers located in Alamance County, North Carolina, and is sponsored in part by Harris Educational, makers of reinventing science kits like Reinventing Edison Build Your Own Light Bulb.